So what we just witnessed in the last two examples is the central limit theorem. The central limit theorem states that if we start with a population with a given mean and standard deviation and take samples that are sufficiently large, that's important, sufficiently large, that the distribution of the means of those samples will be approximately normal. So not truly normal, but approximately normal. And then we have a given mean and standard deviation. So this is actually on your formula sheet. I want to show you that really quickly. If you go to the formula sheet, under the normal distribution, it actually has here the mean and standard deviation of the sample mean. So whenever we're talking about sample means, the mean of our sample means is the actual mean, as we saw in our examples. And that standard deviation is going to be the original standard deviation divided by the square root of n. So that we actually see as our sample size increases, our standard deviation will get smaller. Now the mathematical reasoning for that exact formula is given here. You don't necessarily need to pay attention to this, but if you wanted to know why it is we divide by the square root of n, it's here. All right, so there are two possibilities for the sampling distribution. If our original distribution is normal, then our sample mean is also normally distributed. If the original population is non-normal, then we're just going to use the central limit theorem to get approximate normality. So I'm going to show you guys that central limit theorem one more time in action using StatCrunch. So let me minimize this. Cool. We're going to do an applet, and we are going to, do a distribution demo. Nope, not that at all. Sampling distributions. Haha, because we're sampling. So I'm just going to start us with a uniform distribution. So what this is basically emulating is our dice rolling experiment. So everything is equally likely. And remember, when we were doing the dice rolling experiment, we talked about a sample of size 4. So if we did that one time, you'll see here it is grabbing 4 different samples from our population. All of these samples ended up being pretty small, so our sample mean was also small. We could do that again. Now we're a little bit closer to having something that's a little more balanced. Again, right? And we could do this 1,000 times. And what we're starting to see is exactly what we saw in the question with, or in the dice example, which is we're centered right at the middle, which in the dice example was 3.5 and is now 25. And we're starting to see something that is symmetric, unimodal, almost looking normal in this case. Actually, the dice is one we did too. Sorry, 4 was the next one. So that's for a nice little symmetric distribution. In fact, with the symmetric distribution, that central limit theorem requirement of 30 is a little bit much. You don't necessarily need 30 to get something that looks approximately normal, as you can see here, if you started with something symmetric. But if you start with something like our next example, which was that weird bimodal distribution with the big old gap, or a multimodal distribution with the big old gap, that looks something, that's a terrible drawing. That looks something like this, right? Pretend. And again, this time we had a 4. We could do that once. We could do it 1,000 times and 1,000 more times. And you can see that gap basically disappears because when we average everything out, our mean is right in the middle of that gap. So we see most of our data ending up actually there. So you can see we still have some funkiness going on in this graph, right? It is definitely not approximately normal. It's actually still multimodal. It's just got different new modes, like this little one. It's very strange. But if we take a sample of size 30, and we do this, we can do it once. We can do it 1,000 times. Now we don't have any of that funkiness. We see a nice, tight, normal distribution, a hell of a lot narrower than the one we saw with 4. So the nice thing about this little distribution is you can draw any this applet is you can draw any distribution you want. And you guys can always log into the StatCrunch and do this yourselves. So you could draw something that is very right skewed and then see what happens. If you took a sample of size 5, you see a right skew barely in your sample mean distribution. But again, as you get larger and larger here, you're going to start seeing approximate normality.